So actually, I was going to do a derivation practice on this one, but I'm actually going to ask you to go back into it because it's a good practice. Also, the kind of thing we did last two lecture on the Gibbs energy change over temperature pressure. And here is a good one of doing a self-practice on it. And I have the answer in the PowerPoint, but it would be good for you to go back, try to see if you can do it. I can start off the strategy here. So here is the question. So one thing that very often you will be used is if you raise the temperature of water. And we all know the vapor pressure of the water will increase. And eventually to a point where the vapor pressure of the water will match the atmospheric pressure, then you start oil. So that's something we discussed. Now, and we can pretty much just draw an experimental line. Let's say if we never learned anything about thermodynamics, I'm just pure experimentalist. I can put a glass of water and in a chamber that's sort of a vacuum initially, and then the water will evaporate. And I should have a barometer measure the pressure of the water. So let's say I'm a 18th century, 19th century scientist. I'm curious about this. So I can start plot this stuff up. I can say, okay, on 20 degrees, I got a spot. 25 degrees, or some kind of spot, 40 degrees, this and that. So this is all the thing that I did. Now I draw this beautiful plot. And of course, before you understand nature, before we come up with any mechanistic understanding, the early days of scientists, they just use mathematical tool to simulate what the graph really means. So they have to, because we know the vapor pressure and the temperature are the two parameters that we're considering. So in this case, vapor pressure is a result of radiant temperature. So I'm trying to find out how vapor pressure is a function of temperature. That's basically someone 18th century sometimes pounding in the laboratory. So this is the setting of the question. I'm setting this up for you. I want you to figure out. So obviously now we already know Gibbs energy. Now I want you to, so you can always try to curve fitting, right? Go to your little calculator and you do a bunch of curve fitting. You will probably get something out of this. And when you do the curve fitting, you'll find a very good, the more spots you have, the better curve fitting you'll get, right? And you can actually get a very good mathematical formula for this. Especially nowadays, we have this fancy way called machine learning, right? It's pretty much the same. The more spots you have, the more observation you have, and the computer says, yeah, I can figure out, you give me some parameter, I can figure out how to predict at any given temperature what pressure would be like at phase well. But one problem with machine learning is that we don't really learn anything about the mechanisms behind it, right? I mean, it's a statistical learning. It's a purely number crunching. Now, we want to take a different approach. And we actually have a principle to follow. As we're moving along to this point, what is the principle that we have to follow? Because we have to stay on the line of the experiment. Every new temperature measured, we have a vapor pressure. What principle guides us to derive equation? Because if you know there's actually underlying physical or principle of nature that we can use, then we can derive this equation not by machine learning, even though we can do it today, because of all this fancy computer technology. But still, we have a way to go after this relationship starting from a principle. I want the class to help me to identify what is the same, because there's a constraint. When you derive equation, there must be some sort of constraint that we can use. That is, as long as we're all talking about the vapor pressure for a given temperature of liquid, what was the all the observation points must follow one thermodynamic principle, which is what? That is, all these points on this curve share one principle. I just talked about the phase diagram earlier. This is part of phase diagram. I took part of it.
The points are at equilibrium between the temperature and the vapor pressure.
You got very close. That's,
yeah.
So basically you're saying the vapor pressure, vapor and the liquid is at equilibrium.
Yeah.
Okay, good. So then let's say, all right, but we're still trying to, that's a very good starting point. I think, you know, so we try to find out this. Now we know these curves mean this, we have this. So they're at equilibrium. So then what does that really mean? But they're at equilibrium means what? We need something to get to this point. Austin? Okay, we're getting somewhere. Get molar Gibbs energy of gas. And molar, look at this. Right, pretty good. So we're on to something. But we still haven't quite figured out. And we know every time we move from one point to another point, what do? We change temperature pressure. So that's as a temperature, one temperature pressure. So then we go another temperature, and then we get another Gibbs energy. Let's call this prime at the two. They have to be equal, right? So good. So we start convert a statement or observation into something we kind of have some grasp of it. So we say, hey, well, that's true. So Kalia says they are at equilibrium. Austin says equilibrium means Gibbs energy, molar Gibbs energy of gas and liquid should be equal. So all the points should follow that. Now that should give us something to look into, potential chance to find out whether this, that is the pressure temperature cannot be independent. They have to follow the rule, right? That's the rule. That's where, so they must follow some, how can we mathematically describe this using the principle that they must follow? So you, then we'll go, okay, well, how do we change the Gibbs energy if we change temperature pressure? The last one. So last point. Anybody? What? The equation. Okay. So, yeah. So if we use molar, we put molar there. Okay, we see we are sort of logically walk from experimental observation to go back to the principle we have been discussing, to convert the principle into thermodynamic concept we have used, and then eventually we started to hinge upon what the thermodynamic parameter, how they can relate to temperature pressure. Now this is the point I'm going to stop. You can think of, for every changing temperature or tiny temperature pressure, both phase will change, right? Just like what we did over here. Now see if you can actually go home, work out, work as far as you can to come up your solution, to learn that. So eventually your job is find out how pressure change is related to temperature, which means you'll be sitting here, you're the 19th century scientist who did all the experiments, you can do all the curve fitting you can, and you got some sort of equation. Your job really is to say, oh, I can't measure all possible temperatures. I just want to get a curve. Next time someone comes back and tell me, I have a water at 68 degrees. Can you tell me what the vapor pressure would be like? Well, at that time, the purpose, you can go back to your faded equation. You say, yeah, you go, I can tell you what that is. That's one way. And you can do that way. You can use machine learning. Here, I want you to be mathematically using this principle to derive so that you can have equation say, hey, at any given temperature, I can tell you what the vapor pressure would be like. So that's the class assignment. The answer is in the PowerPoint. You can give it a try. Then if you finally feel like either you get it or you had enough of it, you can take a look at it. And then we will finish the discussion on Friday. Hopefully this is kind of fun, and more importantly, I want everybody to understand the thinking process rather than go diving into the equations right here. Or chemistry 432. I'm not sure about if this is something that up to the level of the high level discussion of AI, but let's use this gas phase vapor equation as example. So I'm just going to draw that very quickly here and then see what this is. So here the discussion we have focused on last time is we are talking about a pure experimental observation one can make or you can experience. That is, if you have, that's just water, right? If you have certain temperature, you can measure the water pressure. So let's put it here. You can imagine an experimental device more or less like this. You don't have a very good one, but so this is good. So you have a beaker, and you have some water in there. And you can control the temperature by heating, and you have a device to let it out, and you can connect it to some kind of barometer. Let's just say. So probably this kind of device, it can be some liquid or mercury. So by the difference of this, you can measure the pressure, here is the temperature, right? So you can do this. This is, think about, we're just going back to early 19th century. So one day we're in the laboratory, we just say, hey, we're curious about, because we know when the temperature is higher, the vapor pressure of the water will be higher. So we can start to experiment without knowing anything about physical chemistry for the moment. So you start plot. So you use a certain temperature, certain pressure, so on and so forth. So you measure a lot of experimental points, and so you started to generate a curve. I mean, that's a much better curve over here. So obviously, the early days of the experimental scientist is find what we call quantitative relationship. We measure, right? So in this case, you clearly see that P, T are correlate. So that means they are not independent. There's they change together. So, or in another way, you can say P must be some kind of function of T or vice versa. So, with the computer, 18th century, we don't have computer. We just kind of, well, we also do some algorithmic simulation. But nowadays, you can pull up your little calculator. There's a little program called curve fitting. Right? So what that is, it'll just produce a particular function. Then you can plug in temperature, and it'll produce a pressure. So that's all done, all good. And so in principle, I mean, one can argue this is probably the early days of, we shouldn't call artificial intelligence, but of some sort. Because the computer can start to tell you a mathematical relationship that reflect your experimental behavior. obviously, in this case, we don't go into the question of why, right? So this is one approach to explain experimental data. However, last time we have discussed a little bit, so I don't want to repeat it, but that's why I'm just going to want to review a little bit what we have arrived at the end of the last lecture. That is, we know if we follow the train of the thought of the thermodynamics, when we use the argument of phase equilibrium or phase transition. So if this is the gas phase, this is the liquid phase. I'm generalizing it for the moment. We know when you have a particular temperature, the vapor pressure on top of it is at that pressure. That means they are equilibrium, at equilibrium, right? So that means we have already established from a long 3 or 4 weeks argument that we can describe this phenomena using an entire different language that we have worked hard on. And we knew this language are true because we know they are as true as we have demonstrated, like a gas would diffuse in the vacuum, or as true as what we said, a mathematical expression of A minus B squared has to be always larger or equal than 0, right? So that factual statement is so true that you have no doubt about it. Now, that same truth has already led us to something a little bit symbolic expressed as, okay, the molar Gibbs energy of the liquid and the molar Gibbs energy of gas as equal. So this is, just think about, this is something we have worked hard to get here. And we also said that if you actually move a point to another point, what you're actually doing is you're shifting temperature and pressure, right? So we also established how you can shift a system's Gibbs energy by shifting the temperature or pressure. Obviously, since right now we're thinking about molar Gibbs energy, so all the term in this expression can be replaced with the molar quantity. So there will be molar Gibbs energy, a molar volume, and molar entropy. So let's just put a little suffix. So this is pretty much where we stopped last time. Now here I'm going to continue a little bit. Just show how we can arrive a functional connection between the two parameters by this argument. And last time we also, I'm basically just still reviewing. Last time I sampled a suggestion from the class. We have all agreed upon the way we think about this is that we will stick. We knew this is the condition we can use to restrict. The reason they are correlated is you can experimentally observe they are correlated, right? But mathematically, you know they are, the reason of their correlation is due to they must be always the same. And from here, since we're trying to relate P and T, then you kind of have to naturally go to the point, well, whenever you shift the Gibbs energy, the temperature pressure can shift them in such a way, then immediately this equation gave you a hint how you can use this constraint to constrain the relationship of temperature pressure. Does that logic make sense to people? Is there any question, we can raise your hand, because this is a very important argument to this point. We're going to use to derive the rest of the equation. Okay. Now, so obviously here, the rest of them is a little bit mathematical, pretty simple one, because for the gas, if we think this is a tiny change of the temperature or tiny temperature pressure, you just make them so tiny, so small, then you can basically use this one, right? So if initially they are the same, they moved into a new place. Let's just call them this new point That's at the tiny point. Then they have still be the same as the right. And of course, everybody changed from where they are in the beginning. So this liquid molar Gibbs energy changed from the originally by whatever the small amount. And the original the same, the new the same, that means when they change are also the same, right? So that's basically so, and we can basically for each of the small change for both gas phase, both liquid phase, now we can just put in the dg and liquid phase equals dg and gas phase. Which also means we can come over here. Basically, that means what is the DGM? Basically, now we can let's put a liquid here. dP S then put a liquid here equals to Vn gas P. Right? So now we kind of already know why the pressure and okay. I don't like that. So let me rewrite it. Okay, so this basically is what we're going to use, and the rest of the derivation actually I just don't want to repeat it, but we can pretty much just write it out here. So okay, I just realized that this argument does not have to be restricted to gas and liquid. In fact, they can be any phase. And so the sample exam question was related to the graphite to diamond change or carbon change. So basically here, the derivation in the slides that I'm using is much more generic. Here I was trying to just make a point to use the gas phase sweep so it makes more sense. But you pretty much can use the same argument over there. So I'm just going to rewrite everything to, instead of chance. So here in this case, obviously, if you use dP dt, the reason basically we have to use some argument over here. So there is a calculation because the delta S molar gas phase, which is the molar gas phase, the molar liquid phase, can be expressed if this is tiny enough. This basically you can think of it as just reversible heat of the temperature at which at this temperature is at, right? Because it's so tiny step, and the evaporation at and also the pressure was regarded to be constant because it was just the temperature almost didn't change. So in this case, you can just simply put it into the delta H. We use the vaporization here, but in the more generic expression in our slides here, we use a phase transition. This will become very useful next week when we use some biological system to talk about this. Okay, so that's one thing we use. Let me see what else we use. Yeah, no, that's really what it is. And the volume, of course, is just the molar volume would be simply just the volume of the gas and the volume of the liquid, right? So if you put all of this thing in, then you would actually get the equation down to there basically is that in our case we have a vaporization and the so as I pointed out, if you want to study for this phenomena, it's probably good to use this derivation in the slide, because the credit of this was given to two scientists. I don't know what they did, because I was trying to Google find out the historical background of how they came up with this idea. I couldn't, so I can only imagine that's what they were doing, sitting in the lab first, trying to pull out a curve, first did some curve fitting, then probably eventually used the thermodynamic argument to find out that pressure and temperature is actually related to each other by some intrinsic physical chemical principle. And of course, you don't need to know what it is to be able to curve fit in it. But the fact is you can actually come all the way from another angle, arrive a similar mathematical relationship between the pressure and the temperature. So, so this is referred, yes, Connie?
In the generic one, so it says it's delta TRS V, and does that mean like going between, like transitioning between two phases?
Yeah, basically it's transition from phase 1 to phase 2.
Okay.
So that's just, I think when I prepared the slides, I try to be more general, because this is what you'll be using to study not just the water evaporating. You could study two solid phases change each other. And more importantly, next week, one lecture I will devote to currently very hot topic in biological community. We observe inside the cell, there are areas form what we call oil-like droplet, and people have speculating that that is a major biological regulation that we have ignored for many years. So this is referred as a phase separation in the intracellular space. So so we want to spend a little bit of time talking about, because it was a very, very exciting topic back then. Now, so for that, to study that, to understand that, you want to use this more generic derivation. But my point here is actually using, because I felt like this was something that I can imagine how initially Clausius Clapeyron got interested in this topic, and how the earlier scientists stared at this graph and trying to figure out how to explain it. And then we can actually arrive at this conclusion by thermodynamic means. But nowadays, a high schooler, in fact, I challenged my son doing this. It would have a high school fair, right? Science fair. I mean, they all do fancy stuff nowadays, but I just asked him to reproduce 18th or 19th century science by using a curve fitting to do this, and I asked him to comment about artificial intelligence and how we should look at it. Now, let me get that point before I go conclude today's lecture. So, in fact, let me finish the discussion here. Oh yes, I forgot that. There's actually more important application in the special case of liquid gas transition. You can actually basically this vaporization would be way more gas, but way more liquid, right? But for gas-liquid comparison, generally speaking, you can almost always represent this as just a gas. Well, for doing so, then you can actually arrive at a very interesting equation where you can have delta vaporization, then you have basically, you can just put it in gas, molar gas. And then if you assume this is ideal gas, then this So you can then plug this in. And so this would be so RT squared, but the P would flip up and then it will come over on this side. And this will give you, run out of room to write it, but I'm just going to put it on the slide because there's no point from here. But this is more fundamental point how we get here. Again, don't worry if you can't see it. This part I derive is exactly the same here. I want to use this. I'm actually more anxious to make it the key point I want to focus on today. This derivation here is all shown here in very detail. Okay. So what I'm trying to use this example to talk about this impact on computation and also how this can influence the future of human existence. Because people get worried, like, well, geez, artificial intelligence will be completely taken over by machine. Now, I think this gives us some insight if we look on this one more carefully. I mean, I'm not trying to say this is artificial intelligence, not at all, by no means. This is just curve fitting, okay? And you could come up many, many different functions to fit this curve very well. And so I'm not going into that. But you might say, gee, well, if you observe enough of this, you could come up something like this equation. For example, you say, well, let me just rewrite d log t dt del h evaporation RT squared. Now let's just say you can do. Let's just assume your computer is so powerful, you gave them all kind of parameter. Obviously, in this case, you have no idea what the del HP is. You probably just call them constant number 1, and you probably call this guy constant number 2, right? Because that's the nature of computer simulation approach. That is, they can take a black box approach to simulating a data curve. So this, you can think of this as the data. This is, and then the correlation of the data is your training set. So you will tell the computer every time when you get this T, I get that P. So that was my observation. The observation is usually limited. But of course, the more observation you have, the better the computer can do to tell you how they can come up with equation. You can throw in all kinds of equations. Any mathematical formula you can think of, you can throw at the computer because the computer is so powerful, they probably will arrive at this formula. And then you might say, gee, you know what, shoot, we don't need any human mind anymore. Because anything we do, we spend all this trouble, 3 weeks, probably computer can do this in 3 minutes. So that's why we all marvel about the power of the computer, also at the same time feel being threatened by artificial intelligence. But I would argue the way we did this way is still showing that the rational approach cannot be fully captured by a computer, at least not now, right? So I said, even I can approach to this point. I can flip this question. It says, okay, I get this equation. I'm going to try to figure out, I did all this experiment with water, right? And I got a good, beautiful curve. I can just simply flip the question. It says, what about ethanol? Well, you might say, gee, well, okay. All right, so let's have a competition with the computer. Sure, we all heard about the beautiful story of how Google's AlphaGo beat the best Go game player in the world. Well, you didn't hear about that? Only the probably Asian kids, we play that game a lot. So we think that it's so complicated. It was a very popular game in Japan, Korea, and China, where you have 331 points, and you have a black and white button, and you try to play your strategy. And then the computer is so good, we putting the best player in human lost to the computer because they compute things so quick. I'm pretty sure if we do the curve fitting, we're not going to beat the computer, but I would have to change the rule of the game a little bit. In this case, I'm saying, oh, I'm not trying to compute the curve fitting. I'm not competing with the same thing repetitive, but I'm going to switch the question. I say, if I'm a human, I have an intelligent understanding of nature in such a broad breadth so that I know the fundamental how nature works in principle, because I know the equation I'm deriving here is the same principle as gas will evaporate in vacuum, not come back. Or in mathematical terms, we said it was the same principle of a minus b squared will be always larger or equal than 0. So use that very fundamental concept, but in such a very complex manner, we arrive this approach to explain this quantitative relationship. So how I'm going to switch the game with the computer? I'm asking the computer, how about the quantitative relationship of ethanol, the relation of vapor pressure and the temperature? The computer might say, gee, you know, I can't do anything unless you give me another set of this data. They're going to lose, right? Because they have to go back to lab, first generate the data. Let's just say they have a robot going around, and the computer says, go robot, you go do there, and the robot still have to go do that. They say that I'm a human, I have computation. I say, all right, okay, actually, we already measured the enthalpy of evaporation of the ethanol. So I can come up with the equation immediately without doing any further experiment. Make sense? I'm not saying that that was the argument that I'd like to present in front of artificial intelligence scientists. They may not like it, but my point here is that don't get me wrong, artificial intelligence or computer-based approach to solve complex problems is very powerful. It's driving a lot of technology modern in society. But they definitely lack the depth and the breadth of the knowledge integration like we humans do. So therefore, we have a much more adaptive ability to cross the field when the previous data or exploration has not reached yet. And all the computer do is they look back retrospectively using all the data we already have. And then this is, in this case, this. And they can actually build up a good model without molecular or physical interpretation of the meaning. Now, the physical interpretation meaning you might say is sort of unnecessary, right? Because you say, well, what's the point? Your whole point is trying to predict something, right? So in that sense, you would argue if my computer can do a very good job to predict the same way as the computer beat the chess player in human, because the game is fixed. The rule is fixed. So they can definitely learn what's already fixed better than us. That's true. So if you have a task that's very repetitive, doing the same thing with more pattern, sure, you should ask computer to do it for you instead of spending your valuable creativity on those things. However, when you want to think this more deeply, you can see that if we have a better understanding what is really driving these, the physical force behind it, in this case, the laws of some dynamics, then we can arrive at more quantitative, more mechanistic interpretation. And that gives us advantage in terms of what? Well, in terms of when we cross over outside the range. In this case, what I mean by that is we don't just talk about water evaporation. We talk about ethanol. Well, then even more so, I was just talking about, we can go through even the graphite diamond phase transition. And then the computer will lose because they need retrain themselves with the new data sets. Because they have no idea that C1 is actually one experimental approach. As long as you measure the evaporation heat, you're done. Whereas with the computer, you take that approach, they would have to collect hundreds of thousands more points with a new matter. Then they will do simulation again. So with that, I just want to basically, this actually, last time I was going to conclude this, let you do this, And I was just on my way home, I heard about this discussion about artificial intelligence. Then I just started thinking about this. I felt like I want to share this with you. So I did a lot more talking myself because this was a new thought come to my head when I was driving to school this morning, so I changed my plan today. Any questions? Does this make sense? Or would you, I mean, it's open. It's my opinion. I want people to kind of chime in if you disagree with me.